So in this lesson we are going to be looking at what a resultant force is. Now the first thing that you need to do is you need to look at this picture. There are two forces acting on this duck. I would like you to consider which forces are acting on this duck. If you need to pause to have a little think about that, you can now. Okay, so the forces acting on the duck actually are up thrust, pushing up. It is the force of the water against the duck, pushing the duck out of the water, and the force acting downwards is weight. Now it's important that we refer to this force as weight, not mass or gravity, as weight is the force due to gravity, is the force that that duck feels. Okay? Okay, so far you will understand that force is either a push or a pull. Now at GCSE we need to develop our understanding of what a force is, and you might have covered this a little bit earlier on. A force is when something influences an object and that object then has a specific change. So for example, if I was driving down the road and I put my brake on, that influence of my brake causing frictional forces makes me slow down. So a force makes things change. Okay, a force causes things to change. It could be slow down, it could be speed up, it could be fall quicker, or it could be fall slower. But it makes things change. It's whatever that influence is that makes things change. Now we've got two different types of forces. We have contact forces and non-contact forces, both of which you should be relatively familiar with from Key Stage 3. Now again, something you should be familiar with from Key Stage 3 is that forces are measured in newtons, represented by that big capital N. There is a new equation that we have to become familiar with today, and that is that force is equal to mass times acceleration. So all this means is whatever the mass of an object is, multiplied by the acceleration of that object, will always give you the value of that force on the object. Now you know what a force is, we need to understand how we're going to model our forces. So the way we model our forces is we draw free body diagrams. Okay? Now, as force is a vector, and you've done this earlier on, force is a vector, this means it has a magnitude and direction. So what we need to make sure is, in our force arrows, we need to make sure that we include a arrow, a direction of the arrow, a area where our arrow is pointing. We also need to include the size of the force. Now the size of your arrow should be proportional to the size of your force. For example, if I had 1,000 Newton force, I would possibly draw a 10 centimeter arrow. And if I doubled my force to 2,000 newtons, my arrow would change from 10 centimeters to 20 centimeters. So if we make the force bigger, we have to make the arrow bigger. If the force is smaller, the arrow has to be smaller. And this is the key part about a free body diagram. They must have an arrow indicating direction, and the size of that arrow must be proportional to the size of the force. Now you know roughly what a free body diagram is. I would like you to read that question below and watch the video of how I draw a free body diagram of forces represented by a paragraph of writing. When we want to draw a free body diagram, we need to make sure that we make the center, the object that we're looking at, a pretty classic shape, because we're saying all this mass is acting in one point. It's all centered at one point. So there is our gymnast. Now the question tells us that there is a weight of 80 newtons. Now for this, I'm going to need to draw a downwards arrow, because weight will always be acting downwards, as it is the force due to gravity. And for this question, I'm going to make it approximately 4 centimeters long, like so. arrow on, label it with the words weight and the value of the force. So because I've drawn this arrow as 4 centimeters long, we're basically saying every centimeter is equal to 20 newtons. That's the scale of our diagram. Now the next part of the question tells us that she is suspended motionless in midair. Because she is motionless, that means the two forces must be equal. So whatever that upwards force is, must have a total of 80 newtons. Those forces must be balanced. Now it tells us that there is 2 ropes attached, so that means there's going to be 2 forces moving upwards. So that means because I know my total force at the top must be 80 newtons, each force moving upwards must have a value of 40 newtons. Now, as this is a force within a rope holding any object, we refer to that force as tension. So I'm going to draw my 2 tension forces on my free body diagram. Now, because 1 centimetre is equal to 20 newtons, I need to draw them with approximately 2 centimetres length, as that is the size of my force. Like so. Label them both as tension with their force value, 40 newtons. And there you have a free body diagram. Here are 3 questions for you to attempt drawing your own free body diagrams, as I did in the video previously. Pause the slideshow here, have a little attempt at this, and then the answers will be up on the screen momentarily. Here are the answers to the following questions. If you need to pause the slideshow at any point or rewind, feel free to. Okay, for question 1, we have a rightwards force of 20 newtons is applied to a book in order to move it across the desk with rightward acceleration. So because we have a book, we're going to count that as another point object. So just draw a small little box to represent your book. Now this time we have only one force acting on the book, which is causing the book to accelerate towards the right. So I'm going to draw a rightwards force of approximately 20 newtons, and I'm going to draw that with about 2 centimeters in length, as such. I'm going to label that force as a rightward force, as we have no other name, and give it its value, where also put in a scale, 1 centimetre is equal to 10 newtons. And there is your answer for number 1. That is how you would draw a free body diagram for number 1. Okay, for question 2, we have a skydiver with a weight of 100 newtons. So first things first, we're just going to represent our skydiver as a small square in the centre. That is our object. Okay, no point drawing a full skydiver, it just wastes time. Now to draw a free body diagram, we need to account for the direction of these forces. So weight is a downwards force due to gravity. Now because it's 100 newtons, I think a nice scale for this would be 1 centimetre would be equal to 20 newtons. Therefore, because we have 100 newtons, we should make the length of our arrow approximately 5 centimeters. We're going to label that as weight and the value of the force. We now need to do the same for air resistance. Now, because air resistance is equal to the weight, we need to also have a 5 centimeter arrow above, like so. label it as air resistance, and the value of the force. Now, it mentions in the question that she's travelling with a constant velocity. This is because these two forces are equal. This is something you're going to look at a bit more in a second, but when the resultant force of an object is 0, they will either be at rest, still, or travelling at a constant velocity. And that is question 2. Okay, question 3. Now this one is a little bit more difficult because we have a lot more forces in play with this one. So we have a car accelerating down the road with a driving force of 120 newtons. The frictional force of the road on the tyres is 30 newtons and the car has a weight of 500 newtons and a reaction force with the road of 500 newtons. So first things first, we need to draw our car. Obviously I'm not going to draw a car, I'm just going to draw it as a box. Easier, much quicker way when we are drawing free body diagrams. We now need to decide on an appropriate scale. Now an appropriate scale here, I believe, would be saying that 100 newtons would be equal to 1 centimetre. So that actually means what I can do now is I can work out the size of my arrows. So my driving force, I can say, would be 1.2 centimetres. Reasonable size for an arrow, not massive, not tiny. We can also say that our frictional force would be around 0.3 centimetres. Quite small, but it represents the frictional force quite well. Our weight acting downwards, because it is the force due to gravity, with it being 500 newtons, would be 5 centimetres. And our reaction force of the car on the road would also be 5 centimetres, as it is balanced. So when I go to draw these arrows now, this is what it should look like. First one being approximately like that. Label it as driving force 120 newtons. We need to draw our frictional force, which is 0.3 centimetres, looking something like that. A very, very small force, but when considering the forces acting around it, would make sense. And we label it with the value of the force, which is 30 newtons. Now we need to draw our weight on, which, as we've already said, is going to be 5 centimetres. So draw it all the way down to 5 centimetres. Label it as weight with the value of 500 newtons. And then finally adding in the reaction force of the car on the road. Again, labeling it with the value of the force. And there you go. There is your free body diagram for possibly the hardest type of question that you might see in this lesson. All from a written description. Okay, so now we know how to represent forces as a diagram, turn it into a free body diagram. We need to understand how to actually calculate our resultant forces, how to find out what a resultant force is. So before we can do that, we need to understand actually what a resultant force is. A resultant force is basically the overall force that is acting on an object. Now, we have certain planes for this, so vertical forces can be summed up and horizontal forces can be summed up. This just means up and down and side to side. So when we're looking to calculate a resultant force, we will look at our vertical plane or our up and down plane, and we will add all them forces together. Now, because some of them forces are pointing in a different direction, that means, for example, our downwards forces should be negative, or it could even be our upwards forces as negative and our downwards forces as positive, however you choose to represent them. So what you need to do is you need to add these forces together. This would be the same for forces in the horizontal plane. So for example, I have some food on a plate there. Now that food is got a downwards force of 10 newtons. So because that weight is 10 newtons, the downwards force is 10 newtons, I need to then account for the upwards force, the reaction force against it. And let's say if my downwards force, my weight is 10 newtons, this would mean that my reaction force would actually be minus 10 newtons. It's going in the opposite direction. So when I bring these together, 10 plus minus 10, for example, will just give me 0. This means that the resultant force of the food on my plate here would just be 0. There is no resultant force on that object. There is no force there causing a change in the object, which is why the food on that plate stays nice and still. Okay, so now it's time to have a go at a harder question, a question that's more likely for you to see in your exam. So down below here we have a plane, okay, or a fighter jet, whatever you want to call it. Now the motive force, the driving force, the pushing force that's pushing it forward, the thrust, is 2000 newtons, and the air resistance or the drag on that fighter jet is 500 newtons. We need to work out what the resultant force is and what direction it is. So to work out the resultant force, we need to add them together. Now these two forces are not pointing in the same direction, and because they are not pointing in the same direction, that means one of them has to be minus. Just for the ease of taking it away, I'm going to make my 500 newtons be the minus. So therefore then, if I'm to put these two forces together, if I'm going to find out the resultant force, the sum of these forces, I need to add them together. So 2000 plus minus 500 just becomes 2000 minus 500, which then gives me my answer of my resultant force of 1500 newtons. Now we also need to work out the direction of this. So if you think about it like this, because it is positive, therefore it must be pointing towards the positive direction, and in our case the positive direction was the right. If it had been negative 1500 newtons, that would have meant that it would have been to the left in the negative direction. But because we said that the right was positive, this means that because it's 1500 newtons as a resultant force, it is going towards the right. Okay, have a go at these additional questions here of calculating resultant forces. Now, what I'd recommend is pausing the video and actually working these out yourself, because the answers will be following now. Okay, so now we know how to calculate resultant forces, we know how to represent forces on free body diagrams, we need to actually know what the effect a resultant force will have on the motion of an object, on the movement of an object. So for example, when my resultant force is 0, let's say there is no forces acting on an object on a table, all the forces on it are 0. If that object is still initially, it will remain still because there's no forces acting on it. There is nothing causing a change on that object. The object stays still if it was initially still. Now, if that object was moving at a constant speed, for example, a car driving down the road at 30 miles an hour, let's say the frictional forces and the driving forces are equal to one another. we have a resultant force of 0. Because that resultant force is 0, there will be no acceleration on that object. And that links back to our equation F equals ma, force equals mass times acceleration. Because that resultant force is 0, that acceleration must be 0. Now that also goes for deacceleration. That object therefore cannot be speeding up and it can't be slowing down. Because the object cannot be speeding up and it cannot be slowing down because its resultant forces are 0, so its acceleration is 0, this means that object will continue moving at a constant speed. So that object will move at the same speed until there is a resultant force placed on that object. And that's probably the most difficult part to wrap your head around. So as long as you can understand that because that object was moving at a speed and now there is no forces causing a change, that object will remain at that constant speed without change until a resultant force begins to act on it. Now you also need to understand what happens when the resultant force is not 0. So if the resultant force is not 0 and the force is causing an acceleration, typically that means it's getting faster. That's if we have a positive acceleration. But if we have a negative acceleration, what we will also get is we will get a process called retardation. It's basically the opposite of acceleration. It's where the object begins to slow down. So it's not accelerating, it's not getting faster, it's instead slowing down. And this is a key term to make sure you remember, that retardation is the slowing down, where acceleration is the increasing of the speed, retardation is the slowing down of the speed. We also may get a change of direction when the resultant force does not equal 0. This is when the acceleration begins in the opposite way. So if that object begins to move in the opposite way, we will then begin accelerating that way again. So 3 different effects for when our resultant force does not equal 0: acceleration, retardation or change in direction, and 2 effects when our resultant force is 0, that it will either remain still or it will remain at a constant speed. Here are some past exam questions based on resultant forces that will involve you applying what you have learned in this lesson. Now, what I would advise you is they will be up on the screen for about 10 seconds. I would advise you to pause the screen to answer the questions. This is by no means a timed task. Take as long as you need to on these questions. The answers will be up at the end. Well done for attempting those questions. There was some tricky ones and some not so hard ones in there. Now, firstly, question 1, we had describe the movement of the man when the resultant force on him was 0. As we just explained not long before, when the resultant force is 0, therefore that means he will either be staying still if he was still initially, or he will be continuing at a constant speed. Now in this question it already said that the man was swimming in the sea. Now when you're swimming you're not still, typically you're moving. So we can assume that this man was actually moving forward. So therefore what we can assume is that when the resultant force is 0, the acceleration is 0, so the swimmer would be moving with a constant velocity. Okay, so this question was quite a long one. I've put it into 2 parts. Question 3 is where a student investigated the frictional force of an object on a surface. He pulled a small wooden block across different surfaces. The block was pulled at a constant speed in a straight line. Pulling the block causes tension force in the string, as we've talked about before. Tension is what happens when we have rope or string that becomes tight. The student kept the angle of the string the same each time. The diagram represents the block being pulled across the carpet. So I wanted you to complete these sentences. Force has a magnitude and direction, so it's a vector. Anything with magnitude and direction will always be a vector, and a quantity with magnitude only is a scalar quantity. Scalars will only ever have a value. They only have a magnitude. They have no direction. They can't be positive and negative. Only vectors can be positive and negative. Part B, two forces acting on the block are tension and friction. Name one other force acting on the block. So for this one, if you think about them four forces that could possibly be acting in all directions, we've got tension and we've got friction. We could have also accounted for weight or reaction force. Both would have been viable subjects. Okay, when the student pulled the block with a constant force, the velocity did not change. Now, because the velocity did not change when the student pulled the block with a constant force, what's the best explanation for this? Force is directly proportional to velocity makes no sense here. It does not apply whatsoever. No work is done by pulling the force. We know that when you pull something, when you move something, when you apply a force and it moves a distance, that we do work. So that is actually incorrect. The block is moving in a straight line. That doesn't explain why the velocity doesn't change. That just tells us that the block is not moving in a straight line. The resultant force on the block is 0. Now that explains it perfectly. It's traveling at a constant velocity because the resultant force is 0. There is no force causing an acceleration, so speed remains the same. Question D was give two control variables in this investigation. There was three possible control variables that you could have talked about in this question. That was that he kept the same angle at all times. Could have been that he kept the same speed at all times, or you could have even said that he kept the same block at all times. Okay, final question. Now this will be done in 2 parts, so just carry on listening and carry on watching for the second part. The diagram shows a person using a device called a jetpack. Water is forced downwards from the jetpack and produces an upwards force on the person. State the condition necessary for the person to be able to remain stationary in midair. So for that person to remain stationary in midair, that means we don't want that person to be moving. So that means we don't want to have any resultant force. So the key part of this question being that the resultant force needs to be 0. You can also additionally explain this in a bit more detail to make sure you get that mark by saying that the forces must be balanced. That would have got you the mark for that question. 5BI, the person weighs 700 newtons and the jetpack weighs 140 newtons. Calculate the combined mass of the person and the jetpack. So all you needed to do was you needed to add these two weights together to give you the total force of that person, the total weight of that person. So 700 newtons plus 140 newtons just gives you 840 newtons. So we know the total downwards force, the total weight of that person is 840 newtons. And as you have done in previous lessons, we're going to use our equation weight is equal to mass times gravity. So if you divide your weight by gravity, this will give you your mass. So assuming gravity is 10, we do 840 divided by 10 to give us a mass of 84 kilograms. Okay, final question. Bearing in mind that we now know what the mass is of that person and jetpack combined, if we increase the upwards force of 1,000 to 1,850 newtons, and it causes the person to accelerate upwards, can we calculate the acceleration of the person? So this is just a summary of everything we've done so far about resultant forces. We need to calculate what the resultant force is on this person. So if we increase the upward force to 1,850, we need to find out what that resultant force is. So we're going to do 1,850 newtons, take away the mass of our take away the weight, the downwards force of our person and jetpack combined. So 1,850 take away 840 newtons leaves us with a resultant force of 1,010 newtons upwards. So now what we can do is we can use the equation F equals ma, as we have looked at this lesson, and rearrange it to give us acceleration. Acceleration is just equal to force divided by mass. So if we put our force in as 1,010 divided by our mass of 84 kilograms, because we know that the combined mass of the person in the jetpack is 84 newtons, gives us an acceleration of 12.02. Now, also wanted the units, so our actual answer for this question would have been 12 meters per second squared.